physics students, so in today's video we're going to learn about how to apply our kinematic equations to better understand car crashes. In this case, we're specifically talking about stopping time and distance. So in your driver's ed course, you probably learned about the 3-second rule, which is that you should keep a 3-second following distance to prevent rear-end collisions. So the question is, why is that? Why is this valid? So let's talk about stopping time first. The average driver takes about 1 to 2 seconds to react to their surroundings. Let's say they see something in the distance like an animal crossing the road. They'll take about 1 to 2 seconds to react before they actually start hitting the brakes. Now, in order for us to solve these problems, we also need to know the average braking acceleration. So, of course, it depends from car to car, and also as cars are getting more advanced, the braking acceleration could be quicker, but it's on average about -4 meters per second across the board. If we were to take all the cars' braking accelerations and average them out, that's the value we would get. Now, obviously, if you hit your brakes a lot harder, it could be a higher braking acceleration, a bigger magnitude, like -5 maybe, but that's also very uncomfortable. As you know, if you've hit your brakes really hard in reaction to something on the street, and also it's not very good for your car. And so we're just gonna use this standard value, -4 meters per second, because that's pretty much the average braking acceleration across the board. Now, if we were to take this information and we were given an initial velocity, we should be able to solve for the time that it takes for a car to come to a complete stop and support the 3-second rule. So let's go ahead and practice one problem. Let's say that in this situation, we're just traveling at a really nice and easy 25 miles per hour. Now, in physics, our standard unit for velocity is meters per second, so I'm going to convert that to meters per second, and 25 miles per hour turns out to be about 11 meters per second. And we can actually solve for the total stopping time. How long does it take for you to see something, apply the brakes, and actually come to a stop? So let's say that our reaction time is 1 second, giving ourselves the benefit of the doubt, just to remind ourselves, average reaction time is about 1 to 2 seconds. But I'm just gonna say we're quick with it, we're super focused, and we're gonna take 1 second to react. Now the braking time is how long does it take for the car to come to a complete stop once you start applying your brakes. So for this one, we need to keep in mind that the driver has started hitting the brakes, and our acceleration in this situation is going to be -4 meters per second. So our givens then would be that our initial velocity is 11 meters per second, our final velocity is 0 meters per second because we're coming to a stop, and our acceleration is going to be -4 meters per second, just a constant acceleration once you start hitting the brakes. That is your acceleration until you come to a stop. Our unknown in the situation is going to be your time, and now we need to figure out what equation are we going to use. So here are the 3 kinematic equations. Off the bat, we can probably rule out the ones that do not solve for time. So I look at this bottom one and I don't even see time here, which is my unknown. That's not going to help me. So now we're down to 2 equations that have time. And the next thing I'll ask yourself is, which equation only has 1 unknown? So, for example, if I'm looking at the second equation, I don't know time, obviously, but I also don't know the displacement. So that's not going to help me because I have 2 unknowns and it's just going to get messy. So I'm going to go ahead and not use that equation. This top equation is perfect because I have the velocities. Initial is 11 meters per second, final is 0 meters per second. I have the acceleration, -4 meters per second. I'm only solving for 1 unknown, which is time, and that matches up. So that is the equation that we are going to use. So now I'm going to substitute my values. So like I said, our final velocity is 0 meters per second because we're coming to a stop. Our initial velocity is 11 meters per second because that's the velocity we're starting at. And then acceleration is -4. And then we're multiplying that by our unknown, which is time. So the first thing I'm going to do is I'm just going to subtract 11 from both sides so that I can get closer to isolating t, which is what we're solving for. And if you divide both sides by -4, you get that the time is about 2.75 seconds. And now we can actually take our reaction time plus our braking time to find our total stopping time. Okay, so total time is going to be equal to 1 second, our reaction time, plus our braking time, 2.75. So our total time before we come to a complete stop is 3.75 seconds. So as you can see here, this is even larger than your 3-second following rule. But of course, when you think about it, there's another car in front of you that's probably, moving and coming to a stop, and they're going to be traveling some distance. So if you're talking about two cars that are moving forward and they're about to come to a stop, it works out pretty well. Okay, now if you're going to be stopping in response to something in the distance like an animal, then you probably will be hitting your brakes a little bit harder as you get closer to the animal. But hopefully this helps you better understand your stopping time. Of course, it's going to differ based off of your starting velocity. Maybe in your mind, you can start thinking, if this velocity was higher, how is that going to impact our stopping time? So you can obviously just replace this 11 meters per second with greater numbers, and you should be able to, in your brain, in your head, just kind of think about how is that going to impact our total stopping time. All right, but what about stopping distance? How far do you travel when you are reacting and you're braking? It's actually quite interesting to take a look at this calculation. So stopping distance is, just like stopping time, composed of two segments. There's going to be a reaction distance when you detect the hazard. So in this case, it's like an animal. It could be another car that's stopped in the distance as well, but you react, and as you're reacting, you're still driving your car, so you're still moving, okay? So there's still a constant velocity because you haven't started hitting your brakes yet. So you can see from the sticker tape, these dots are equidistant from each other because you're still traveling at a constant velocity. Now, once you're able to react, okay, then you actually hit your brakes and you start to slow down, and that is called your braking distance, okay? So in total, your stopping distance is your reaction distance plus your braking distance, and that's how far you're going to travel before you actually come to a stop. Okay, so the average driver takes about, again, 1 to 2 seconds to react to their surroundings before they apply their brakes, just like we talked about with stopping time. And as we know, the average braking acceleration is -4 meters per second per second. Again, if we're given this information and initial velocity, they should be able to solve for the total stopping distance for a car. All right, so let's go ahead and look at one of these examples. Again, I'm just going to use my 25 miles per hour or 11 meters per second initial velocity to help us better understand how to calculate a stopping distance. And then, of course, if your initial velocity changes, you can still apply the same technique to solve for the total stopping distance. So just to remind ourselves, our reaction time we're going to be using is 1 second. That's going to help us with the reaction distance. And then we're just going to apply all of our other givens as we move along. So in our reaction distance, what is important to remember is that a driver has not started hitting the brakes yet. At this point in time, they're just noticing something in their environment, and they're still traveling at their original velocity. So it's a constant velocity is what we're going to say. Okay, so our givens would be our velocity is 11 meters per second, and that's just a constant velocity. Our acceleration is 0 because we're at a constant velocity, and our time is 1 second because that's how long that we are traveling when we're reacting to our environment. Our unknown in this situation is now displacement. How far are we traveling during our reaction time? So let's go ahead and take a look at our kinematic equations and figure out which one we want to use. First thing is we can rule out the top equation because there's no displacement there. It doesn't make any sense. We don't want to use that one. And the bottom equation, I'm also going to rule out because there's two different types of velocities here. Technically, we could use it because our final velocity is just the same as our initial velocity, but I mean, it's just going to be a little bit not as clean to solve for it. So this one you could use, but I like using the second one just because it's directly solving for displacement. It's just easier. You don't have to manipulate things around. You have all the other givens, so that's perfect. So we're just going to go with that second equation. So again, here are my givens, my unknown, and here's my equation. I'm going to go ahead and plug in my givens into my equation. So displacement is equal to initial velocity 11 times the time 1 second plus 1/2 times acceleration is 0 and time again is 1. This whole thing is just going to honestly cancel out because there's a 0 that's multiplied to the other numbers. So really our displacement is going to be 11 times 1, which is 11 meters. All right, what about the braking distance? So the braking distance is how far is the car going once we start hitting the brakes and it's braking until we come to a stop. So in this point in time, we're actually going to be accelerating, which means a change in velocity. In this case, we have started hitting the brakes. Our acceleration is going to be -4 meters per second per second. So what are we given? We are given our initial velocity is going to be 11 meters per second. Our final velocity is going to be 0 meters per second because we're coming to a stop. And our acceleration is going to be -4 meters per second per second. We are still starting to solve for the displacement equations. Let's take a look. So let's see, I want to solve for displacement. Again, the top equation is going to be pretty useless because there's no displacement up there. And then we have these two other equations that we could use. In this situation, I do not have the time value. I don't know how long it takes to come to a stop. Of course, if I solve for the time where I use the time from our initial problem, stopping time, I could plug that value of 2.75 seconds into this equation. But if I'm not given it initially, this second equation is not going to help us. So in this situation, if I hadn't solved for the stopping time already, the only equation I could use, thank goodness we have options, is going to be our third equation down here because we have the final velocity, the initial velocity, and the acceleration, and the only unknown is going to be the displacement. So I'm going to use that third equation. Boom, there it is. So I'm going to now plug in my givens into the equation. So final velocity is 0, we're going to square that, is equal to initial velocity 11 squared plus 2 times the acceleration -4 times the displacement. So very first thing, I'm just going to go ahead and square out the 0 and the 11. So 0 is equal to 121 plus 2 times -4 is -8 times the displacement. I'm going to go ahead and subtract 121 from both sides. I'm not showing this on the slides, but I'm just explaining. I'm subtracting this from both sides, so I'd get -121 is equal to -8 times the displacement. Then you divide both sides by the -8, and if you do that correctly, you can try that on your own. You should get a displacement is equal to 15.125 meters. Now your total stopping distance, similar to the total stopping time, is going to be equal to your reaction distance plus your braking distance. So total distance again is equal to my reaction distance, which is 11 meters. I traveled 11 meters just when I was reacting, plus the braking distance, which was 15.125 meters. The total distance is going to be 26.125 meters. Now my challenge for you is to think, if my initial velocity was higher than 11 meters per second, how is that going to impact my total stopping distance? What do you think is going to happen? And how would you apply that to your driving? Now, the final thing is, what if you were distracted or drunk when you were driving? So there have been so many studies done to see how distracted driving, like when you're texting and driving, and drunk driving affects reaction times. And I'm sure in your mind, you can imagine it's just going to ruin your reaction times, okay? So given our understanding of this presentation, this lesson, you should be able to start thinking about how is that going to impact your total stopping time and your total stopping distance. But it's even more interesting to be able to solve it on your own and see with numbers, with actual velocity values, how is that reaction time and distance changing? How is the total stopping time and total stopping distance changing if you are distracted or drunk versus just normal driving? So I encourage you to try that out and let that kind of impact your driving decisions as well. Thank you so much for taking the time to watch. I hope that was helpful, and I'll see you in class. Bye.